So consider the equation x squared plus 1 is equal to 0. All right, now there's no real number that can make that true because there's no real number whose square is negative. So we manufacture one, we come up with one, and we say that the square root of -1 is an imaginary number. Well, it's not imaginary, it's certainly a number, and we use it in many different branches of math, electrical engineering. It's a very useful number. Notice though that we have a plus and a minus, and since we just made this number up, we don't really know which is the plus and which is the minus. There's no difference, in other words. The point of that is if your problem doesn't concern itself with the imaginary number, if your problem doesn't mention the imaginary number, then there should, in your answer, be a symmetry between I and negative I, because it doesn't make a difference which one we call it. Okay, so we can multiply this imaginary number by any real number, call it b actually, and we can add any real number to that. So this is our general complex number, and a complex number is often denoted z. Z is often used as a complex variable, just like x is often used as a real variable. Okay, well, this lends itself to visualizing real numbers on a Cartesian plane, where this is the real part, the a, and the vertical component is the imaginary part, b. So a, b, and here's the number a plus bi. Well, there's more than one way to put coordinates on a plane. You have the Cartesian coordinates, but there's also polar coordinates, theta and r. So how to write our complex number z using our polar coordinates theta and r? Well, we need to translate. A, this length here, is r cosine theta, and b, this length here, is r sine theta. So z is a plus I times b. Okay, take the r out, and we get r cosine theta plus I sine theta. Now, I'm going to digress for a bit and just take a look at this piece of it. And to do that, I'm going to use what's called the Maclaurin series. The cosine of theta is the same in a region around 0 as its own value at 0. So the cosine of 0 is 1, plus the value of its first derivative. Derivative of cosine is negative sine at 0. Value of negative sine at 0 is 0, divided by 1 factorial times x. The second derivative of cosine is negative cosine, and its value at 0 is negative 1. It's the second term, and x squared. And then the third derivative will be 0. The fourth derivative, 4 factorial x to the fourth, and the Maclaurin series takes shape. And if you are not familiar with the Maclaurin series, I'll have another video on that. Do the same thing for sine. The value of sine at 0 is 0. The first derivative of the sine is the cosine. The value of the cosine at 0 is 1. So that's 1 over 1 factorial times x. Second derivative, negative sine. That value at 0 is 0. Third derivative, negative cosine. So plus negative 1 over 3 factorial x to the third. And the pattern takes shape. And so on. Do the same thing for, and this may seem like it's coming out of absolutely nowhere, but e to the I theta. Well, we know how to take derivatives of this, so we know how to take a Maclaurin series. The value of e to the I theta at 0 is 1. Its first derivative is I e to the I theta. The value of that at 0 is I, so plus I over 1 factorial, which is just 1, x. Second derivative is negative 1 e to the I theta, negative 1 over 2 factorial x squared. Okay, third derivative is negative I over 3 factorial x to the third. And the next one will be back around to 1, so the pattern takes shape now. 1 over 4 factorial x to the fourth plus I 5 factorial, and so on. Now notice, these terms match up. These match up except for an I. These match up. These match up except for an I. These match up, and so on. So we've shown that e to the I theta is cosine theta plus I times sine theta. Euler was brilliant. There are formulas and theorems named after him in many different branches of science. So, but this shows us how to rewrite our complex number here. There. All right. This is a very useful form of writing the complex number when we're dealing with powers. The nth power of z is r to the n e I to the n theta. So the magnitude of a power of a complex number is the power of the magnitude of the original complex number. The angle of the power of a complex number, called the argument of the complex number, is the multiple of the angle described by the power. So if we take a power of 2, we double the angle. Let me show you an example of this. I'm going to draw in the complex plane a number 1 over root 2 plus I 1 over root 2, chosen so that it has a magnitude of 1 and an angle of 1/8 of a turn. All right. And you can search online for videos on why I prefer the symbol tau to the symbol pi. There's some really good videos on that out there. And let's try to square this number. So this is z, and let's evaluate z squared. The square should be the imaginary number. So let's check that with the what's de Moivre's formula. So the magnitude here is 1. 1 squared is 1. The argument, that was 1/8 of a turn. Twice that is 1/4 of a turn. And yes, that is I. If we go a quarter of a turn around and up 1, we get I in the complex plane. There we go. What really gets interesting is when instead of a whole number power, we have a fraction, or a root. A fractional power is a root. So, let's take another example. Let's say -8. It's a complex number. It's just a purely real complex number. And let's evaluate the 1/3 power. All right. So, what is -8 as far as the r theta form? -8's way out here. That's a half of a turn, and the magnitude is 8 e to the I tau over 2. There we are. To the 1/3. 8 to the 1/3 is 2. And we have e to the I tau over 6. So magnitude 2 and a 1/6 of a turn right about there. Yeah. Alright, now if you're paying very close attention, you should be saying that's wrong. The cube root of -8 should be -2. Hold on a minute. This is not only a half of a turn, it's 1.5 turns. E to the I, 3 half turns is 2. 3's cancel. E I tau over 2. A half turn goes around to the negative number, so we do have -2. -2 is a cube root of -8, and this is 2.5 turns. E I to the times 5 tau over 2. 1/3 is 2 e 5/6 of a turn. All right, and our question did not involve I, so we see a symmetry between I and -I, a top-bottom symmetry. Another very interesting fact that I came across when researching this video is this. I to the I. What is that? Well, what is I? I is 1 e to the tau over 2. All right, is equal to I. Now, raise that to the I, and we get e to the negative tau over 2. But I is not only e I to the tau over 2, it's 4. Slipped into my pi thinking again. I is not only e to the, there's a quarter turn up, it's 1 1/4 turn up, it's 2 1/4 turns up. So I to the I is an infinite set, e start with a negative quarter turn. Oh, sorry, down. Yeah, negative quarter turn plus any full number of turns, either positive or negative or 0. There. What's really interesting is I raised to the I is not just a real number, it's an infinite set of real numbers.